So thanks very much for the introduction, and congratulations on what seems to be a really fun day. I saw all the beers and stuff outside. So I don't know if I'm the last talk, but I'm certainly after plenty of beer, so just sit back and relax. It's an easy topic. So what I want to tell you about today is about a pretty aggressive, global, technological race, the race towards building a large-scale quantum computer. Maybe we can start by a quick show of hands. Who here heard before about the concept of quantum computing? Okay, the vast majority, pretty much everyone. I entered this field in 2003, so 23 years ago. I left to do my postdoc in the US. And back then, quantum computing was an academic secret, if you like. Not just that most of my friends did not hear about it when I tried to engage them over a beer about telling them what it is. The reaction was sort of, mediocre, not very excited. Today, most people are very excited about quantum computing. And the first part of my talk is really to tell you what is the big deal. Why are people excited about quantum computing? So first, to convince you that people are indeed excited about quantum computing, what I show you here is a global map of the government investments in quantum computing programs in the various respective countries. You see here just examples. The total sum in 2025 mounted to $54 billion, and as you can see, almost 30% of that comes out of China. Most developed countries have programs towards developing quantum computers in their own country. Israel just finished a 5-year program, which was budgeted at about $0.4 billion, and now there are discussions, and in fact, it's even beyond discussions. We're about to launch our next phase of quantum computing program with a sum which is almost as much. If you'll notice, you'll see that while China has an investment of $15 billion, the US only has $6 billion in government investments as of 2025. Can anybody guess why? How come the US allows itself to have an investment which is about a third? It's private, exactly. In the US, most of the investment is not done by government, but rather by the private markets. So on top of the $54 billion which is spent by governments globally, there's almost a similar amount of investment, probably even larger, which is done in the private sector. That includes venture capital, pretty intensive investments, several billions annually, as well as all of the hyperscalers. So if you look at Intel, if you look at IBM, if you look at Google, if you look at Amazon, all of them have in-house operations, R&D operations towards developing quantum computers. Israel has a rather lively ecosystem of quantum startups, actually. So quantum computing is a big deal. People take it very, very seriously. Why do people take quantum computing very seriously? And the reason that people take quantum computing very seriously is that quantum computers outperform any other computer that we have on Earth, okay? That would dominate any other computer that we have on Earth. What do I mean by that? What I don't mean by that is I don't mean that these computers are going to be faster or smaller or necessarily more energy effective, even though they will be much more energy effective. What I mean by that is that there are problems that today we can't solve at all, and with quantum computers, we will be able to solve these problems. So most of you here are computer programmers, right? So you know a little bit about complexity theory and computer science. Some problems are problems that in order to solve them, what you need, the number of steps you need to go through, is polynomial in the program size. These are programs that we believe computers can solve, of course, depending on size, but for pretty large size problems, computers can tackle them. Some problems are exponential problems, and because the number of steps goes like 2 to the power of the number of bits the problem is defined on, they're considered hopeless. Quantum computers can take some of these problems and reduce them from exponential complexity to polynomial complexity. Let me give you two examples. One example is the example of taking very large numbers and breaking them towards their to the product of prime constituents that composes them. The reason this problem is important, as most of you, I guess, know, is because this is the algorithm that lies behind public key cryptography. Public key cryptography is the protocol that allows us to send the key which is public, but even though we have the encryption key, that key does not help us at all in order to decrypt the information that we encrypted. In order to do that, what you need is a mathematical operation which is irreversible. It's not symmetric in terms of performing it one way and performing it the other way. Multiplying very large numbers to get a big number, which is the key, is an easy operation, but taking a very large number and breaking it into its prime constituents is a problem that no classical computer knows how to do in polynomial time. Quantum computers can take very large numbers and break them into their prime constituents in polynomial time. So this is a very good example of why governments take quantum computing very, very seriously. When I did my postdoc in 2003, the main funding agency behind that research was the National Security Agency in the US. Okay. Here's another example. Let's take a very large molecule. What you see here is rendering of the penicillin. But you can take any other complex molecule. And let's ask ourselves, how can we assemble this molecule from all the atoms that compose it in a way which is optimal in terms of energy cost? Okay? Why is that interesting? So, can anybody guess what is the largest contributor to energy consumption in producing wheat? Is it transportation of wheat from the field to the consumers? Is it transporting the water which is necessary, tractors in the field? What is it? Fertilizer. The largest cost is the synthesis of fertilizers. Today, we feed most of humanity based on agriculture that is based on synthetic fertilizers. The protocol for synthesizing fertilizers or ammonia that we use was invented over 100 years ago by a chemist from Berlin. His name was Fritz Haber. In fact, he was on his way to be the scientific director of the Weizmann Institute, but didn't make it. He died en route in Basel. He was already in his 70s. He was also a war criminal because he initiated and led the chemical warfare of the German army in World War I. But he did save humanity from hunger. He was able to tell us how to synthesize fertilizer and scale up agriculture. But the process that was discovered then, over 100 years ago, is by no means optimal. If we can produce fertilizers even with 10% less energetic cost, the impact financially, environmentally, and in terms of energy consumption is going to be huge. So why not do it? We know what atoms compose, these molecules are composed of. We know how many electrons each one of the atoms has. We know what are the equations that govern the dynamics of electrons, so we know how electrons bind themselves into a molecule. Let's push these equations into a hypercomputer, crunch the numbers, and get the answer of how to synthesize these molecules in an energy optimal way. The reason we can't do it is because this is, again, a problem that requires exponential resources to solve. By the way, the reason this problem is exponentially difficult to solve is that this is a quantum mechanical problem. And the number of pathways we need to follow, the number of pathways that quantum mechanics allows for, is too large to count. It's exponentially large. Okay? So if we could do that, and quantum computers can do that, being on their own quantum machines, if we're able to do that, the impact would be huge. And these are just two examples. We know of problems that come from material engineering, that come from finance, comes from logistics. Crypto, we've already discussed. Cryptocurrencies rely on the RSA protocol. AI, all these fields have problems which we either know or believe that we can solve much more efficiently than classical computers. And that is the reason that private businesses, the venture capitalists, and governments are extremely excited and want to make sure that if a computer like this is built, they'll be the first one to build it. So after I've convinced you that quantum computers are a big deal and they're important, the next thing I want to tell you is what is the relation between quantum mechanics is a physical theory, and computers. Computers are these machines that execute these abstract protocols, information processing. What is the connection between physical theories and computers? And the connection has to do with the fact that information, at the end of the day, is physical. When we encode information in digital bits, we often forget that these bits are physical objects. They're little switches that have two physical states that represent either 0 or 1. That can be a light bulb, which is, can be bright or dark, representing 0 or 1. But at the end of the day, it's a physical object. And when we download a movie through Netflix or Apple or whatever is your favorite content provider, and we download gigabytes of information into our cell phone, what we often forget is that we actually download tens of billions of physical objects that go into our phone. They transfer from a server through optical fibers, and they have physical representations in our machines. Back in the 1950s, when computers were built from vacuum tubes, or the processing units were built from vacuum tubes, it was very difficult to scale to bytes of information, gigabytes of information. But today, we have technologies that scale transistors to the 3-nanometer scale, and that's why we can pack billions and billions of transistors on a single chip, and we can scale information processing to really large scales. But at the end of the day, these bits obey the laws of physics. Now, which laws of physics do these bits obey? And the answer is that when you go down to the microscopic scale, if you could think of bits that are nanometric in size, if you eventually can think of bits that are encoded on single atoms, the laws of physics that govern the microscopic world, the laws of physics that atoms obey, are the laws of quantum mechanics, okay? So the relation between information processing and quantum mechanics is that information is physical. We use physical means to transport, store, thank you, and process information. And we do that on an ever-growing smaller scale. And at the very small scale, the laws of physics that govern the behavior of information-carrying devices is that of quantum physics. So that brings me to the third part of my talk, which is a crash course on quantum mechanics. What are the laws of quantum physics? Now, Murad told me I only have 40 minutes, so if I had an hour, we would go through all the equations behind quantum mechanics, but because we're limited to 40 minutes, I'll try and focus on what is in my mind the main differentiator between the physics at the microscopic scale and the physics on the macroscopic scale as we experience it and is described in Newton's laws of mechanics. So we already agreed that we store information in these physical switches. They're bits. And bits can be in one out of two physical states, one representing 1, the other representing 0. This is not a liability which is obeyed by quantum objects. Quantum objects that have two states do not need to choose. They don't have to be in one state or another. They can coexist in two states simultaneously. And it doesn't matter which states these are. It can be two positions. We engineer situations in our lab routinely in which atoms are in two positions simultaneously. If that bit is a little magnet that points north to represent 0 and south to represent 1, a classical magnet needs to be in one physical reality. It can either be in 0 or 1. Okay? Quantum magnets can be in two different directions simultaneously. They can point north and south at the same time. Two colors. We can be either yellow or red. Quantum bits can be both yellow and red at the same time. In fact, any reality that we can think of, quantum objects can be in multiple of those realities simultaneously. Okay? Mathematically, we describe it through waves, the mathematics of waves. We call this the superposition principle. But at the core of this phenomena, quantum bits can be both at 0 and 1 at the same time. Now, if you hear that fact, that quantum systems can live in multiple realities simultaneously, and your jaw doesn't drop, that means either you've heard that before, or you haven't listened carefully to what I said. But that's the best description of nature that we have as of today, okay? So we've already understood the main difference between quantum physics and classical physics. Quantum objects can be in multiple realities simultaneously, and a quantum bit doesn't have to be in 0 or 1. It can be in both. That's a twofold advantage as compared to a regular bit. Let's move forward. Let's say I have 2 bits. How many states can 2 bits be in? 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. It's 2 times 2, okay? And if I have a problem that requires searching through all these options, I'll need 4 steps in order to carry out this algorithm, okay? 2 quantum bits, 4 steps aren't necessary. 2 quantum bits can coexist in all these 4 states in a single superposition. That's a 4-fold advantage as compared to 2 bits. Let's continue. 3 bits. 3 bits can be in 8 different options, okay? And if I need to search through this register, 8 different queries. 3 quantum bits can coexist in all 8 states simultaneously. 8-fold advantage. You get the idea here, right? I have an advantage which looks like 2 to the number of qubits that I use, okay? 2 to the power of 100 is almost a number as large as the total number of atoms in the universe, okay? If I would ask the biggest computers today on Earth to calculate, to go through, to search, to send queries, 2 to the power of 100 queries, the time it'll take these computers is longer than the age of the universe, okay? That's never going to happen. The biggest computers we have on Earth today can go through about 2 to the 55 queries in a day. That means 56, 2 to the 56 in 2 days, 2 to the 57 in 4 days, and so on and so forth. It's not a race you can win. It's an exponentially difficult race. A quantum computer would be able to generate a wave which would be spread over these 2 to the 100 different possibilities simultaneously. So for the type of questions in which you need to search very intensively through all the possibilities that a large number of bits can allow for that type of algorithm, quantum computers could potentially give a large added value, because the way they'll work is generating a wave which is spread across all this very large number of options you need to query, and in a coherent way find your answer in a polynomial number of steps, okay? So that's, in a nutshell and very simplistically, the promise that quantum computers bring to the table. Okay, so now that you're all experts in quantum computers, let me say a few words on how these quantum computers are being built. And also, where is this technology today versus where it needs to be in order to fulfill the promise. So what you see here is a little animation, I didn't talk through it, that shows how we built our own quantum computers. My group built the first fully operating quantum computer in Israel. That was about 5 years ago. It was a relatively small quantum computer, 5 quantum bits. The way we build the computer is by using individual atoms as quantum information carriers. We need to start from systems that are very much quantum in their own right. So we use strontium atoms. Actually, the ion species doesn't really matter. We ionize these atoms so we can apply electric fields and confine them, hold them in place. So we fabricate these chips. On these chips, there are electrodes. The electrodes apply electric fields that trap these atoms these ions at very short distances above the chip surface. Now these atoms hover in mid-nothing. They don't touch any surface. They're in vacuum. So the way we interface with our qubits is using laser light. Now we use laser light to do all sorts of operations. One of the first things we do is we use laser light in order to cool these ions to temperatures of about 1/1,000,000th of a degree above absolute zero. Okay, so I don't know if you know, but temperature has an absolute scale. So there's an absolute zero to temperature. Why do people think of temperature in absolute scale? Temperature can be thought of, at least in gas, as the kinetic energy that atoms in the gas have, okay? So it's their motional energy. If you cool them down to a complete standstill, then their temperature is zero, okay? We're at about 300 degrees above absolute zero. So the zero temperature is minus 273 degrees, okay? Atoms around us at room temperature move at velocities of about 300 meters per second, so the velocities of a fighter jet. When we cool our ions down to 1/1,000,000th of a degree above absolute zero, they move at velocities of millimeters per second. But then we use all sorts of other operations using lasers. If you work with quantum bits, first thing you need to do is to reset your register, right? You need to reset your qubits. Secondly, you need to encode information into your qubits, and then you need to carry out the computation. You need to execute logical gates. All that we do with laser light. So our technology is very heavily reliant on optics, lasers, electro-optic modulators, and all the rest of it. Now, today, unlike regular computing, where there's one technology that dominates the market, so the computers you all use integrated circuits that are made from semiconductors, and then these semiconductors realize transistors using junctions. In quantum computing, that race is still open. So there are 5 or 6 different technologies that are competing with each other. One of them is using electronic circuits that are cooled to very low temperatures and then become superconducting, meaning they conduct electricity without any resistance. Another example of our technology used in quantum computing is photons. Another technology is neutral atoms that are trapped in laser fields. Now, what is the best technology among all these modalities? Trapped ions, of course. But I think the question is still open, and I think that the question of whether or not this space would evolve into a situation similar to classical computing, in which one technology takes the entire jackpot, or whether, like different technologies, let's say clocks, different technologies would have different advantages for different applications, and they would coexist, at least for the next couple of decades. I think the jury are still out on that problem. Last thing I wanted to say is, where are we, okay, in this technology? So today, I think across modalities, the largest quantum computers we see have roughly hundreds of quantum bits, okay? there are sort of, very coarsely speaking, there are two parameters you need to look at when you evaluate quantum computing technology. One is the number of qubits that technology has, and the other is the number of code lines that computer can run before errors corrupt the computation. So how deep is the computation, and how wide is the computation? Very, very coarsely speaking. Today we see computers that have hundreds of quantum bits and can execute tens of thousands of code lines, okay? This is already enough, or was enough, for quantum computers to demonstrate quantum supremacy. What do I mean by that? To demonstrate solving problems that regular computers cannot solve at all. These problems were mathematically designed, especially for quantum computers to reach quantum advantage relatively easily, okay? Quantum computers are already large enough for customers to log into cloud services or buy quantum computers and run algorithms that give them results that they can use in their businesses. I was at a lecture recently where a large company, construction company, used the quantum computer in order to optimize on the problem of where to place air conditioning outlets in an industrial huge building they built. This is a problem with 50,000 degrees of freedom and 15,000 constraints. Huge problem. Quantum computer was able to solve it in a way that helped that customer. Could that customer use a very large classical computer to get a comparable result? Maybe, maybe not. We can't answer that question. Where do we need to be in order for quantum computers solve the hardest problems that they promise to solve? Let's say break the most sophisticated encryptions that we have today. So 2048 bits RSA codes, okay? If you can do that, you compromise cryptocurrency, you compromise financial information transfer, you compromise information which is sent between government agencies. You really have a significant disruption in front of you. Up to about a year ago, if you would ask, if you'd go 3 years ago, people would tell you you need 1 billion bits and at least 10 to the 12 code lines. A year ago, people came up with much smarter algorithms and said the answer is much more modest. You need 1 million bits, million quantum bits, and about, maybe 10 to the 9, 1 billion code lines. Okay, that means in order to do that, all we need to do is scale quantum computing technology by about a factor of 10,000. Is that a scary thought? I don't know. My first computer when I was 16 was a Commodore 64. The reason it was called Commodore 64 is because it had 64 kilobytes of memory. When I was a student for my bachelor's degree in Jerusalem, I had a student job in Intel, and we were producing the 486s, which were already about a factor of 1,000 larger, if not 10,000. So electronic computing technology have already gone through these leaps in a matter of a decade or so. So going from 100 to 1 million is not such a frightening thought. But that's a year ago. About 3 months ago, a paper came out showing that with the right quantum error correction technology, you can actually reduce the resource to 100,000 quantum bits. And about a couple of weeks ago, a paper came out showing that with 10,000 quantum bits, you can already break the RSA 2048-bit encryption. That means that progress is not just made on the hardware side, where the number of bits and the number of code lines consistently grows, but also on the algorithmic side, where people are finding more and more efficient algorithms. Today, we're about an order of magnitude away from quantum computers being able to solve the toughest problems that they promise to solve. So this is not a futuristic revolution. The quantum future is already here. When we built the first quantum computer in our lab, we called it White Sack with a Q at the end. And the reason we did that was to give homage to the first electronic computer that was built in Israel. The first electronic computer that was built in the world was built by MI5 in Bletchley Park during World War II in order to break the Enigma encryption. So if you like, history repeats itself. Motivation of strong compute haven't changed much. The first public electronic computer that was built, by the way, the computer that was built in Bletchley Park was classified. Nobody in the public knew it existed until the mid-70s, so it was a well-kept secret. The first public electronic computer was built in 1946. It was called the ENIAC. It was built at the University of Pennsylvania. The first electronic computer in Israel was built at the Weizmann Institute in 1954. And work on that computer started in 1947. Okay? The gap between electronic computing and Rehovot in 1947 is unimaginable. I mean, it wasn't, Israel wasn't a startup nation, wasn't a tech force. There were orchards and, sand in Rehovot. Nevertheless, people had enough vision to make the necessary investments in order to build an electronic computer. Just as a curious, to go through the necessary investments, which were as large as the annual budget of the Weizmann Institute at that time, the Weizmann board assembled a little ad hoc committee to study that problem and recommend the Weizmann Institute whether to embark on that rather expensive adventure or not. That little committee was assembled out of three rather anonymous people, Robert Oppenheimer, John von Neumann, and Albert Einstein. And they ended up recommending that the Weizmann Institute does go. By the way, Einstein hesitated. He wasn't sure that that's the right thing to do. But von Neumann and Oppenheimer convinced him, and eventually Weizmann did build that computer. That computer was immediately put to use for scientific and then other national needs in Israel. And I think that, you look here, Wix is, an amazing example out of many technology companies in Israel that rely on software and on compute. And I think that without that vision, 70 years ago or so, of people understanding that we need to have that foundation in order for knowledge-based technology to grow here, we wouldn't have been here. And that's why we really hope. And today there's already 4 startup companies that spun off Weizmann Institute of Science that are building quantum computers. One of them is a company I co-founded called Quantum Art. And if Wix wants to buy a quantum computer, let me know. I'll give you a friend's price, a discount. But we're very much hoping that the seeds that we plant today in the quantum computing, and I think it's very important for me to say because there are at the national level, there are constantly arguments. This is an investment we need to make now in hardware, not just in software. And that is because quantum computing is such a disruptive technology that we see the walls not going up, they're already high today. It's the kind of hardware that if we don't have independence in making it, we'll never have the ability to import it. So it's very important that we make sure that we have Kahol Lavan, white and blue, quantum computing hardware in Israel. And if we do that, and we already have that to a great extent, we're sure we'll have impact on science, on industry, on security, and on the civil society at large. So that's all I wanted to say, and if you have questions, I'll be happy to take them. Thank you. Questions? No, it's done.
Hey, don't go yet. Do you have any questions?
Where do you store the computer? Ah, good question. We actually had in June 2 Iranian missiles hit the Weizmann campus and destroyed 5 buildings or so. So 2 buildings got direct hits and other buildings got damage, significant damage from blast. I think before we go into and I'll say a few words about the risks of being hit by missiles. Quantum computers in general are not small machines. It doesn't matter which modality you use, they're relatively large. They'll range anywhere between 3 or 4 racks, which looks like 3 or 4 refrigerators, all the way to something which is 3-4 times larger. So they're not small. They're not going to fit into your toasters or washing machines anytime soon. They're high-performance computing, HPC, and people view them as such. So customers who would buy quantum computers are data center that team up these quantum computers to other HPC infrastructures such as GPU clusters, and then the two work in tandem. Okay, so it's not that quantum computers work on their own, they work in tandem with other HPC infrastructure. So they're not small. Now, if you look at most quantum computing companies, they have 2 avenues for generating revenue. One is packing these computers they built relatively tightly, and then deploying them to data centers. And then these data centers can be extremely protected against attacks and so on. Some of the data centers in Israel certainly are. But the other stream of revenue is companies say, I don't want to go through the crazy engineering that goes into deployment. I'm going to build a very good computer, but I'm going to host it. So I can attend to it when it needs tuning, I can attend to it when things go wrong, but then sell computation time and go through the cloud. And then it's your own facility that you need to take care of. At the Weizmann, there are several laboratories that are building quantum computers, including my own. Everything is in regular buildings. Weizmann Institute is not a bunker, and we can't build it as a bunker. So what we need to do is hope that peace would come upon our land, and we'll be able to continue and do science for the future of humanity without having to worry about missiles all the time, and protect ourselves with active protection when we need. Is what? Oh, okay. So the question was whether I think quantum computing is similar to fusion, to thermonuclear fusion, in the sense that it's a technology with a great promise, but we keep on promising, but we never get to the point where it actually fulfills the promise. So by nature, I'm a tech optimist. And, being invested so much in quantum, you can guess that my answer would be not so much on the comparison to thermonuclear fusion, but rather on the fact that I believe we are a short distance away for quantum computers, getting not just bringing value to people, because they already do, but rather solving the toughest problems that they promise to solve. As for the comparison to thermonuclear, I think it's a fair statement to say that people, by the way, for those of you who don't know what thermonuclear fusion is, in nuclear reactions, you get a lot of energy that can be released. One direction of nuclear energy is that of nuclear synthesis, okay? So fission, so I'm sorry, not synthesis, taking large nuclei and breaking them. That's how reactors that generate electricity work. That's how uranium and plutonium nuclear bombs work. But if you go to very light elements, if you take 2 helium atoms and you synthesize hydrogen atoms, and you synthesize them into a helium molecule, you also get a lot of energy. And the nice thing about that energy is there are no radioactive products to that reaction. So it's clean nuclear energy. And the fuel is water. It's hydrogen. It's very prevalent. So that's if you can do that, and you can build reactors that work on thermonuclear reactions, you've solved the energy problems of the world. The sun burns like that. We know how to generate that reaction in an explosion. That's how the hydrogen bomb works. It's a horrible weapon that can wipe out, continents. But we don't know how to do it in a controlled way, and that promise of being able to do it in a controlled way, which would solve the energy problems of the world, is a promise that have been going on for 60 years, and we haven't been able to fulfill it. I think we're not that far away from that point as well. So I'm pretty optimistic that within the next century or so, we will be able to... No, but listen, century is not that long of a time. We will be able to get there. So I think both these vectors would get to the end point.
Well, we're out of time, so thank you very much. It was
Thank you.
very enlightening.